I'm going to kind of give you the punchline for what we did at IARC. As Paul mentioned, I was the chair of the Animal Studies group. And many of the studies that we reviewed, that were reviewed by this group, were studies done out of my laboratory. And I just want to tell you right off the bat, I didn't review my own studies. Okay, these were reviewed independently. So let's go through this table here. And basically what we're looking at is we're looking at a total of 51 studies. And what we're looking at are different categories of experimental situations that affect the circadian system in some way, all right, in this column. So we have a category of alterations in light exposures, and those include continuous bright light at night, or continuous dim light at night, or intermittent or pulsed light at night. There was another category of circadian disruption induced by a chronic jet lag protocol, So what these individuals did was put mice under 12 light, 12 dark conditions. So that's a typical lighting cycle in animal studies, whether it's mice or rats. And what they did was every couple of days, they advanced the lighting cycle by 8 hours. They changed the lighting cycle, kept them on for 2 days, and kept doing that. And that induces an artificial kind of jet lag in these animals. So, and they did that for several weeks. There was another type of circadian disruption induced by performing electrolytic lesions, actually going in with a probe into the brains of these animals and burning out the suprachiasmatic nucleus, burning out that central clock, all right? Then there was another manipulation that you could surgically remove the pineal gland. Remember I said that melatonin from the pineal gland, driven by the suprachiasmatic nucleus, is the best output indicator or marker of circadian activity. So pinealectomy will remove that signal. Then there were experiments done with physiological levels of melatonin. That is, levels of melatonin were used in these animals that mimicked what they would naturally produce during the night. Okay? So it's kind of the opposite of what these manipulations are doing. All right? And then there was another category of clock gene mutations. Remember I mentioned those molecules that cycle in the suprachiasmatic nucleus and also in the peripheral clocks of our tissues that run the clock mechanism? Well, there are ways to cause mutations in specific parts of the DNA in those clock genes that screw up their clock mechanism. And we can look at the outcomes on cancer development and growth. So those are the different kinds of manipulations of the circadian system. Here we're listed the different kinds of cancer models. This is no other exposure, and you can see that all these different manipulations weren't done in this particular category, okay? So for alterations in light at night light exposures, and in the case of clock gene mutations, were done in a small number of experiments in animals in which cancers developed spontaneously. These animals were on a 12 light, 12 dark cycle initially, all right? And then these alterations were made in lighting, or clock gene mutations were induced. And there was, the investigators just let the animals sit there with time and spontaneously develop tumors. And those experiments usually take a very long time. There's another model that's used very commonly in cancer studies in animals, where you take an animal and you induce the formation of a particular kind of cancer by giving a chemical, okay? You can also do it with radiation. That's less commonly done, but usually a chemical carcinogen. Then there is a third category of a tumor model where we actually take tumors that either develop spontaneously in an animal or were initially induced to develop in an animal, and then take a piece of that tumor and transplant it to a tumor-naive animal and document the growth of those tumors. In this situation, in the chemical initiation, just to jump back, what we're doing in those studies is looking at the incidence of animals developing a particular tumor. So we'll count the percentage of animals that develop at least one tumor and look at things like tumor multiplicity. In an animal that develops a tumor, how many tumors does it develop? And you can also measure the size or the volume of the tumors. All right? In these studies, we're putting a piece of tumor tissue in all of the animals. So they're all starting out at the same size. All animals have tumors. So in those studies, we're measuring primarily growth, and as we'll see it a little later, metabolism. So what that boiled down to was, for no other exposure, 75% of the studies showed a positive effect. In the chemical initiation studies, about 50%. And in the cell transplantation studies, 29 out of 31 showed, or about 93%. So of all the studies, we got about a 78% of the studies demonstrated a positive, significant effect on promoting carcinogenesis in these animals. And that's what made the animal studies, the subcommittee ruled this as being sufficient data. It was strong data.